All right, hello, this is Ashton Hill, and this is my submittal for Lab 6 in Embedded Systems, the Control A Servo lab. So I've implemented this on an FPGA using a counter and a pulse generator, and let me just show like how it works here. So I've got this leftmost switch here as my reset signal. So I actually just enabled the device. It's an active low reset. I pushed reset high, so now it's ready for operation. And it goes right all the way to the right as far as it can. Then as I use these switches to say what duty cycle I want to send to my servo, as you know, is servo motor, right? It's a duty cycle to an angle. And I'm just flipping through my 3-bit duty cycle here. And as you can see, we went all the way from the right 90 degrees to the left 90 degrees. So yeah, and then just going back down, proof that this does in fact work. All right, so as far as, that shows it works as far as the code. Here is my servo controller. So as you can see, its inputs are clock, reset, a duty cycle, which I'm giving for my switches, and it outputs a PWM signal. So the clock comes from the board, the reset is that leftmost switch, and the duty cycle are the other 3 slide switches. The way this works is it instantiates a pulse generator component that I wrote, where you tell it how many cycles you want a pulse to go high and how many clock cycles you want the pulse to go low. And it just does that. It just spits it out at you, and I'll show you that architecture here in a second. So essentially what I did is I instantiated this pulse generator, and I looked at the datasheet for the servo and manually put in, essentially like if I want this angle, how many clock cycles do I need to wait on the high pulse? Or so depending on what angle I want, that tells me my duty cycle. I converted this duty cycle to a number of clock cycles high and a number of clock cycles low based off my clock frequency and the servo datasheet. But okay, pretty simple. Just got 2 multiplexers essentially feeding a pulse generator module with one multiplexer saying, hey, if your switches are this, here's how many high pulses you need, and if your switches are this, here's how many low pulses you need. So for the pulse generator module, what we've got here is it just takes a clock, reset, cycle size, cycle so, and pulse, and it's going to go create this pulse based on what you said. I implemented this in a very structural way. I didn't do a good job of using a behavioral architecture here. I'm really taking advantage of the language. I very manually stipulated what kind of devices I wanted. And I'll actually flip over to my Raspberry Pi here to show you this diagram. So as you can see, I've been writing in some VS Code lately. Pull up this pulse generator diagram. So here's how my pulse generator works, is it relies on a counter, a toggle flip-flop, and a multiplexer. And essentially what's going on is when this thing is enabled, so essentially when reset goes high, because enable is just hardwired to 1 here, this up counter starts at 0 and it starts counting up. It starts counting up to whatever I've told it is the overflow valve. So if I've told it to overflow at 3, it'll go 0, 1, 2, 0, 0, 1, 2, 0, 0, 1, 2, 0, so on and so forth. Every time it overflows, it generates a flag, an overflow flag, which controls a toggle flip-flop, which essentially just inverts whatever my output is. If my output is a 0, if I'm in the low end of my pulse, then I'll tell my multiplexer to set the overflow valve to the low cycles. If my output is a 1 though, if I'm in the high phase of my pulse, then, I need to overflow at my high cycles value. And that's essentially just how this works, is however many cycles high I set up a counter to overflow at that point, and when it overflows, it toggles from high to low. And when I'm like low, I overflow at my low value, and that toggles from low to high in my toggle flip-flop. And so finally, I guess I need to explain how does my up counter work. I've got another circuit diagram for that. This one's a little bit bigger. This one, again, I didn't do a behavioral architecture because I wanted to manually troubleshoot some timing issues I was having and make it just as quick as possible. So as you notice here, I've essentially got a D flip-flop that outputs my count and a D flip-flop that outputs my overflow flag. And essentially what's going on is with every current count, there's an adder that's generating whatever the next count should be, and it's passing that into a multiplexer and into a comparator. If my adder output is equal to my overflow val, then what my counter does is it's going to pass a user-defined start value to next count into the D flip-flop. In my pulse generator, I said start val is 0, so whenever it overflows, it's going to overflow back to 0. So if we reach our max, send 0 to next count instead of the adder output, and that's what gets mapped to count the next clock cycle. If we haven't reached our overflow val, then just adder out gets mapped to next count into the D flip-flop and to output. This D flip-flop here essentially just delays the overflow signal by 1 clock cycle. Essentially when I didn't have this D flip-flop, if the overflow value was 3, let's say, it would go 0, 1, 2, 0. The overflow flag would go high around 2 instead of around 0. So I use this D flip-flop to delay the overflow signal by 1 clock cycle. But yeah, this is the implementation of my up counter, which is used in my pulse generator. And my pulse generator pretty much makes up the entire servo controller module. It's just that cycles low and cycles high are fed by 2 multiplexers over here with some hardwired values, and using the slide switches on my FPGA as selectors. But yeah, that is my assignment 6 for embedded systems here at the University of Memphis. I hope you enjoyed. Thanks.